Okay, so today we're going to start focusing on individual elements and how they're organized in the periodic table, things like that. How many of you feel like you're semi-familiar with the periodic table? You've at least seen it before, right? I'm talking about that big thing on the wall. You've seen it before. Maybe you've talked about it in a class before. Yeah. Right? How many of you feel like you're there? How many of you feel like you're experts at the periodic table? Okay, that's good. All right. Tell me, can somebody raise their hand and tell me what an element is? We talked about it last class, and one of our groups presented on elements. Atoms versus elements versus compounds. Can you tell me, Micah, tell me what an element is. Perfect. A pure substance that cannot be broken down into simpler substance. So is water an element? No, because water can be broken into hydrogen and oxygen, right? Hydrogen and oxygen are elements. So everything that's made up, everything that makes up other compounds is an element, and those are on the periodic table. Okay, so if it's not on the periodic table, it's not an element. All right. We're going to take it way, way back here to talk a little bit about history of the periodic table. Okay, in the mid-1800s, there was only 60 elements that had been discovered. And so here we see we're all the way at 115, right? Only 60 of them had been discovered, so about half at that point by the mid-1800s. And then after that, when the scientific discoveries really started kind of flowing. Okay, a guy by the name of Mendeleev, which is a name you need to remember or recognize. Yeah. Yes, please. You should be taking notes over this. You can take notes. I would take shorthand notes. So don't write down every single the that's found on here. Try and make it shorter and put it in your own words. Okay, you do need to know he was the first guy that developed a system for organizing the elements. Mendeleev. Mendeleev. Okay, he developed the first system of organization. What he did was he listed them in columns by atomic mass. And then he grouped them by elements that behaved similarly. I'm going to show you what that looks like here in a second, but I'll give you a chance to get it written down. He ordered them by mass and then grouped them by similarities. And so I'll walk over here so we can kind of see what this looks like. So if you look at the periodic table today, I'll give you. We currently order our elements by atomic number. So I want you to just look at an element to begin with. Okay? An element has a symbol, a name, an atomic number, and an atomic mass. Okay? Atomic number and atomic mass are two different things. We'll cover that here in a little bit. But you see every atomic number, it just goes in order. Okay? Okay? All of these atomic numbers go in order. 1, 2, 3, 4, 5, 6, 7. That's what it's ordered by now, is atomic number. He put it by atomic mass. And then he put them by things that behaved similarly. So his first periodic table looked like this. Okay? He said hydrogen has an atomic mass of 1. Then he had lithium. He didn't have helium yet. Beryllium, boron, carbon. He had a bunch of those in the middle. But he was so smart that he understood there was going to be more elements discovered, and he left gaps in his periodic table for those new elements. Right? He was smart enough to understand that we don't have them all yet, and there's going to be elements that fit into these gaps. And so he left those gaps in the table. Eventually, after he predicted what their characteristics would be, those elements were discovered, and they did fit exactly where he had left a spot for them. Okay, so he was not only smart enough to realize we're going to have more elements, he also understood what their characteristics would be, what their masses would be, and where they would fit into his organizational system. Okay, so smart dude. Again, you guys don't have to have every single word that I put up there written down, okay? Just main points. You need to know Mendeleev. You need to know that he was the first periodic table and that he organized his by atomic mass, okay? Now, once Mendeleev had all of these elements discovered, a guy by the name of Henry Moseley came in and reordered them by atomic number, which is what we currently have them organized by today. So Henry Moseley put them in order of atomic number. And what that did was it allowed the characteristics of elements, things like valence electrons, electronegativity, all that kind of stuff. It made those characteristics repeat at more regular intervals. So it gave the periodic table much more of a pattern. Number and atomic mass. Can anyone tell me what does the atomic number identify? The atomic number identifies the number of what in that element? Not number of atoms, number of protons. Okay, atomic number is the number of protons in that element. And that number is so super specific to its identity. That's like its whole identity is the number of protons. Okay, we're going to cover this a little bit later, but I didn't want to keep talking about it if we didn't know what it was. Okay, so atomic number is the number of protons. That's its number one identifying characteristic. How many protons does it have? Okay, and when we talk about atomic mass, what does that contain? What does that number tell us? The number of protons and neutrons. Okay, do you see this little symbol here, P+? That's how I'll abbreviate protons, because protons have a positive charge. Okay, so the atomic mass tells us the number of protons and the number of neutrons found in the nucleus. Okay, that's where its weight comes from. Its mass comes from the nucleus. Electrons are also contained within an atom, but electrons are so tiny they don't affect its mass, and so we don't count that in the atomic mass. Okay, so electrons weigh so little they don't count into its mass at all. Okay, does that make more sense with atomic mass when we say that now? Atomic number, atomic mass. Okay. Okay, I don't want to talk about that. All right. The periodic table is organized into what we call periods and groups. Groups and periods. Our very most important one are groups. Do we know which way groups go on the periodic table? Side to side or up and down? No. Up and down. Groups go up and down on the periodic table. Up and down on the periodic table. The zigzag line, they're still groups, but within the group there are metals and nonmetals, and that's how it just changes. The zigzag line will tell us something in a minute, but groups go up and down. Okay, the groups are what we call, sometimes they're called families. I don't want you to write that down because I won't use that term a lot. You may see it like in a textbook or in a text I have you read, but I will not call them families, so you don't need to write that down. I just wanted you to hear that once. Okay, groups are based or are organized this way because they have similar chemical properties. So when I say groups, I'm talking about this whole column right here. That's group 1. And all of these elements within this column behave very similarly. Very similarly. Okay, they have a lot of the same characteristics and they behave very similar. Same with this. This is group 2. Right? Beryllium, magnesium, calcium, strontium, barium, radium. That's group 2. They all behave very similarly. Okay? We will label, I'm going to give you a periodic table and we'll label all the groups and we'll do all that, but not right now. Periods are the rows, so rows lay flat, they go side to side. These have properties that change as you move down the row. So rubidium does not behave the same as strontium, which does not behave the same as indium or tin or antimony or any of those. Okay, so as you move across the row, you'll see pretty drastic changes in characteristics. Okay, but within a column or a group, these all behave pretty much the same. Okay, in terms of how well they bond, are they reactive, all that kind of stuff. Okay, you absolutely need to know that groups go up and down. Okay, have to know that. Okay, in general, on the periodic table, elements that are close together tend to behave alike. So I said rubidium and strontium don't have exactly the same characteristics, but they do, they're in the same, they're on the same team, they just don't play the same position, right? They behave similarly, but they don't do exactly the same things. That's kind of the general rule of thumb for the periodic table. Or on the left side of the periodic table, where are nonmetals at?
Right side.
The right side of the periodic table. Many of these nonmetals are gases at room temperature. So take a look at those elements that are in the nonmetal section. Helium, neon, argon. Are those things that are that you're used to being gases? Right? Helium it's a gas, right? All of those in group 8 are actually the noble gases. We'll hit those in a little bit. But all of these are gases at room temp, or many of them. Oxygen. We're used to that being a gas at room temp, right? All of those things, generally to the right of that stair step, are gases at room temp. So there's some examples. If we have nonmetals that are solid at room temp, they're usually really brittle. So what's it mean to be brittle?
Breaks easily.
Yeah, it breaks or it shatters really easily. So examples of nonmetals that are solid at room temp are sulfur, carbon, phosphorus, and iodide. Generally solid at room temp, but very brittle. And so if you're looking at this periodic table on the wall, your nonmetals are your blues and your greens. Okay, if you want to shade that on your periodic table, if you have a second, you can also. Okay, a whole different color. Nonmetals behave opposite of metals. Metals are really good conductors of electricity, so nonmetals are not good conductors of electricity. I want you to think about this question. Why would it be problematic for us if nonmetals were good conductors of electricity? Right, we breathe oxygen. The air that surrounds us is nonmetals, oxygen, nitrogen. If those elements were good conductors of electricity, it would be constantly traveling through the air. That would be problematic for us. Does that make sense? Yeah. Okay. Last little group of the periodic table is the metalloids. So what do we think metalloids would probably be? Kind of metals, kind of not metals. They behave a little bit of each. They have characteristics of each. Okay? They do some things like metals and some things like nonmetals. Most are solid at room temp, which is like a metal. They're not quite as malleable as metals are, but they're not as brittle as nonmetals. So they fall right in the middle of each of these categories. Some of them are shiny, and they are what we consider semiconductors of heat and electricity, which means it travels through them, but it's not super efficient. So there's really shiny antimony, and another picture of that. metalloids in general surround that stair step. Okay, so your metalloids really aren't shown on the wall periodic table, but they are the ones that surround the stair step. Okay, so if you look at this periodic table, it's the greens. Okay. You don't have to necessarily color in the metalloids. I don't think you need to color those in, but I want you to see where they're located on the periodic table. Are we good? So here's where our metalloids are found, surrounding that stair step. You'll notice that all metals here are yellow. All metals are yellow. Non-metals are blue, which includes hydrogen. And then the metalloids are the guys in the middle. They surround that stair step. Okay, I don't need you to shade metalloids necessarily on your periodic table, but I do want you to know that metals are on the left, non-metals are on the right. Okay, that's going to play a big part in when we start building chemical formulas and naming compounds. Okay. Questions about that? Okay, now we're going to go into each of our groups. We're going to start with the alkali metals, and we're going to move across the periodic table left to right. So the alkali metals include group 1. Karis, can you tell me one element that's in group 1? Lithium. Perfect. Stan, tell me another element that's in group 1.
Sodium.
Yes. Okay, perfect. So everyone's understanding where group 1 is. First column. These all have a silvery appearance. They're all really soft. They can be cut with like a knife or a scalpel. And they are not found in nature. They are not found in nature. And I want to talk about why that is here in just a second. This is something that you possibly talked about in your physical science class, and that we will get into with a lot more detail. But group 1 elements have 1 electron available to them in their outer shell. Anyone know what those outer shell electrons are called? Good, valence electrons. Group 1 elements have 1 valence electron, which means they have 1 that is available for them to bond. That's it. Can anyone tell me how many electrons an atom needs to be complete, to be happy? They need 8. Very good. They need 8. And so for group 1 metals, they have 1. That's it. So for their electrons, would they rather get 7 more, or would they rather give up 1? Is it easier to get 7 new friends or to give away 1? Give away 1. Give away 1, right? Maybe I shouldn't use friends as an example. But it's easier to give away 1 thing than to gather 7 more, right? Especially in terms of electrons. So all of these group 1 elements give their electron to anything and everything quickly. And so they are so reactive they can't be found in nature. Because they can't be by themselves. They want to give that electron away so readily that they can't exist by themselves in nature. Okay, does that part make sense? That's why. They are so reactive. They want to give their electron away so someone else takes it. And when they give it away, then they become an ion and they become much more stable.
Is that why, like, if you put it in water?
Right,
Yeah.
right. We're going to look at that.
Are we going to do it?
No.
Why not? That'd be so fun. Just don't watch it.
The group 1 elements are super, super reactive, especially with water. Okay? Because they have 1 valence electron. I've kind of alluded to that already. But we are going to watch this video with the group 1 elements and their reactivity in water. Maybe. Okay.
Please excuse the interruption. Will the following please report to the auditorium? Milana, Claire Lucian, Molly Mason, Libby McFerrin, and Macy Meir.
Okay, here we go. They take on a little bit more of what we would consider normal metal properties. Harder, they're stronger, they're more dense than their alkali metal neighbors. Okay, they are what we would call a little bit more of a metal property. But what's the one that stands out to you here? That seems problematic that it's a metal. Magnesium or calcium. Those are things we ingest regularly, right? Is there metal chunks in your milk? Okay, when calcium bonds with things, it no longer has those metallic properties. So we don't drink just straight calcium in our milk, right? We extract calcium from other compounds, basically, right? We're not just drinking straight calcium metal. All right, these guys have higher melting points. They're less reactive than alkali metals. They are still too reactive to be found in nature, though. Okay, they're less reactive, so they're not going to cause an explosion like the group 1s. But they still can't be found in nature. Okay? If you were going to take a guess, how many valence electrons would group 2 have? 2. Very good. It has 2 valence electrons. So again, is it easier to gather 6 or to give away 2? Give away 2. Right, so it wants to give away its 2 electrons. So there is pure calcium. Again, we don't see that floating in our milk, right? Our body extracts calcium from other compounds that contain calcium. Okay. Any questions with those so far? Yeah, Tim. Sure. Metals, transition elements. These are groups 3 through 12. So the big red chunk in the middle are the transition metals. Okay. They have very typical, or what we would consider typical metallic properties. So I want you to look at some elements in the transition metal region. All the reds or oranges right there. And tell me some that you recognize.
Gold.
Gold. What else? Cobalt, tungsten, mercury, iron, titanium. Those are all ones that we would consider very typical metals, right? If we're talking everyday language, we know those are metals. And so they behave very much what we would consider like metals. Okay, I'm not going to have you write down these metallic properties again. You just looked at those, so we don't need to look at that again. Okay, you know what metallic properties are. In terms of valence electrons, these guys don't follow the rules. So it's not like group 3 has 3 valence electrons and group 8 has 8. The transition metals don't really follow those rules. So they are kind of a variety of valence electron numbers. So the transition metals just don't follow the trends. The hipsters of the periodic table, if you will. Okay, we're going to skip over to group 16 or 6. So tell me what elements are contained in group 16. Oxygen, good. These are called the chalcogen group, or the chalcogen family, group 16. So oxygen, sulfur, selenium, tellurium, polonium. Chalcogen? Chalcogen? I'm not going to guarantee that's the, absolute correct way to say it, but that's how I say it. This group is fairly reactive. And I want you to try to determine why you think they're fairly reactive. If they are in group 6, what does that mean in terms of their electrons? Not 8. 6. They have 6, right? Because they're in group 6. So is it easy for them to give away 6 or to gather 2? Gather 2. Right? When those numbers of exchanges are low, that means that it's a pretty reactive element, right? If I only have to get 2, it's pretty easy. If I would have to get 4 or give 4, a little tougher, right? But if I'm only having to exchange a couple, that means I'm pretty reactive. The group 6 group has a lot of properties because there's oxygen, that's gas at room temp, sulfur, and the rest of them are solids at room temp. Okay, so they're kind of a wide range. You don't have to write. Sorry, you don't have to write this part down. Just listen to what I'm saying here. Okay, so if you look at group 6, oxygen's a gas, sulfur, and all the rest are solids. They tend to form compounds with metals, and most of those compounds do not dissolve in water. Okay, there are 3 nonmetals, a metalloid, and a metal found in group 6. So they are all over the place. Okay, oxygen, sulfur, nonmetals, selenium, tellurium are metalloids, and polonium is a metal. So group 6 has a wide variety of properties in it. Last thing is that they can be man-made. Man-made elements. Did you guys know that there was man-made elements? There are elements that only has been done in a lab, right? And it only lasts for like a little bit, but they are only made in a lab. There are 35 man-made elements. You need to know that number. 35 man-made elements. And they're kind of sprinkled all over the periodic table. But you'll notice ones that have what we would consider familiar names are typically the man-made ones. So, Mendeleevium, probably man-made, right? Probably we named it after the guy who made the first periodic table. What about Californium?
Oh, definitely found that one.
Probably made that one. Berkelium, Americium, I don't know how you say that correctly, but Nobelium. Yeah. Where? Yeah, Newtonium. Okay, so Neptunium. Sorry. A lot of these down here are man-made. Okay, they're what we call the super heavy elements. Their masses. Okay, but there are 35 man-made elements. Highlight that, circle that, whatever you need to know. You need to know there are 35.
35 man-made elements.
35 man-made elements. Gotta know that. Alright, sorry, we talked about that. We only have 2 groups left to get through. Oh, we don't. We'll see if we have. Alright, group 17 is my favorite group, called the halogens. They are fluorine, chlorine, iodine, bromine, and acetine. This is my favorite group of elements. I don't know. They're very reactive. They are the most reactive group of nonmetals. They usually bond with metals from group 1 or group 2 and form what we call salts.
Wait, so it forms salt or
Okay. Noble gases. 8 valence electrons. All gases at room temp. Unreactive. You do use noble gases when we call neon lights. They're typically more than just neon in there. A mixture of the gases and their reactivity and their, I can't think of the word I'm looking for. A mixture of those gases give you different colors of neon lights. Okay, so although we call them all neon, they're not really all neon. It's neon and argon and xenon and krypton that make up those neon lights. Okay, so how are we feeling about the orientation of the periodic table? Was most of it review or was this new stuff? A little bit of each?